not saying I'm going to ask you to come up to the board and do it right now, but just like, yeah, I remember something called completing the square in Algebra 1. All right, so this is a way to solve quadratics. Okay? Basically, the idea is if you know how to solve things that have perfect squares in them, maybe it would be better to take your quadratic equation and make it a perfect square if it isn't already. So by perfect square, I mean that when we go to factor it, everything factors nicely into something squared. Instead of like x minus 1 times x plus 2, it's like x minus 1 squared. One nice package, not multiple different factors. Okay? So these first two are just reminders of how we solve problems when what you're looking for is all packaged inside a squared. So notice that each of these equations, they are quadratics. Right? What makes it possible to solve these equations by square roots? What's unique about these quadratics that's not true of all the quadratics we've seen so far in the unit that makes it possible to solve these using square roots? Okay? Good. There's only one x squared. There's not like an x later on in the problem, right? It's not 3x squared plus 5x. It's just 3x squared plus 5, which means we can get the squared part alone. And once you have something squared alone and you're trying to get rid of the square, what are you going to do? What is the inverse operation of squaring? Square rooting, okay? So that's what we work on doing here. We want to get the squared part alone. So in this first equation, I would subtract 5 from both sides. So I'd have 3x squared equals 15. The squared part is still not alone yet here, okay? 3 is not being squared. X is being squared. So the next thing I would want to do is divide both sides by 3. So I would have that x squared is equal to 5, okay? And then here's where I'd take the square root to see what x is alone. Now, when you are solving an equation using square roots, okay? So, for example, let me do this. Okay. What is the square root of 16? 4. What is the opposite of the square root of 16? Negative 4. If I say you could be positive or negative square root of 16, then I'm saying you could be positive or negative 4. Notice that your answer here was dictated by the problem. When I see square root of 16, do I tell someone, ooh, plus or minus 4? No. The square root of 16 is 4 unless it is signed differently in front of it, right? But it's different over here where we're solving because we're not just taking the square root of 5. We're saying there was a number called x, and when someone squared it, they got 5. So that's like me walking in and say, you guys, I'm thinking of a number. When you square it, you get 16. What's my number? 4 or negative 4. You don't really know, right? Both of those squared would be 16. So when you're solving, when it's some mysterious number was squared to get this, that's when you have to say it could have been the positive or negative version of that. Does that make sense to everybody? So when you're calculating what someone gave you, you use the sign they gave you, and that's the only possibility. But when you're solving, some mysterious thing was squared and got this outcome, it's possible it could be positive or negative, and you need to include both of those. Yeah?
Or like, would that be the one that you wouldn't unsimplify completely? Like, if it was like 4, and on the next one?
Yeah. So, and I'm actually not going to do the next one, but I'll mention that because these are like prereq skills. Yeah, if this was a 4 in here, I wouldn't leave my answer plus or minus rad 4. What would my answer say? Plus or minus 2. So I would still calculate the radical, but the plus or minus I would include because I was solving with the square root. But if I'm just calculating a square root that someone gave me, use the sign that they've already assigned to it. Okay? All right. So we're actually going to skip example 2. Sorry. In the note guide, I put like everything in a perfect world. That was whatever. But our schedule is a little bit different. So. All right. So here's a problem where it's not just x squared. It does have x squared and it has x. Which means if we were going to solve this by factoring, we would actually subtract 9 from both sides, set it equal to 0, and finish that. Okay? But I'm just going to give you guys a little bit of a different perspective. So I'm not saying that what I'm about to do is the only way to solve it. I'm just saying if I wanted to solve this in a similar way that we just solved the last problem, what I want to do is create a perfect square. So notice x squared plus 12x plus 36. That's a perfect square, right? How you can identify things that might be perfect squares, the beginning and the end of the polynomial would have to be perfect squares. So like x squared is a perfect square, and 36 is a perfect square. So then the question becomes, is the middle term what I would get if it was really just x plus 6 squared? So is 12 what you get when you multiply out x plus 6 times x plus 6? Do you get 12x in the middle? Yes. Okay, so that's a perfect square. Right? Again, is this the only way to do this problem? No, you could subtract 9 from both sides, set it equal to 0, and use quadratic formula, factoring, whatever. But today we're looking at this square and square root perspective. Okay, that's our focus of today. So x squared plus 12x plus 36 can be rewritten as x plus 6 squared. Those are the same thing, so it would still be set equal to 9. Now, even though this stuff in here is more complicated than just having x squared, we have the same thing essentially that we had in the last problem. We have everything that we're looking for packaged inside of a perfect square. So if I want to solve it, since I have the perfect square alone, I can go ahead and take the square root of both sides. Okay? If there was stuff that was being added, subtracted, or multiplied to that perfect square, I would have moved them to the other side first before I took the square root. So here, the square root of something squared is just whatever was being squared, so x plus 6. And the square root of 9 is 3, but again, we're going to include the plus and the minus because there was an x inside of the squared, meaning this could have been multiple things that are squared that turn out to be positive 9. Could be 3, could be negative 3 once you square it. And so then to finish solving this equation, I would subtract 6 from both sides. But I want you guys to pay really close attention to what you have on this right side. You really have like too many arithmetic problems, right? You have a negative 6, and then you have a positive and a negative 3 being combined with that, which means you literally have 2 arithmetic problems to do. Negative 6 plus 3, okay, so that would give us negative 3. And then you have to do a whole separate problem. Negative 6 minus 3, which would give us negative 9. So if you're sitting there like, Ms. Dahl, I subtracted 9 from each side, set it equal to 0, I factored it, I got the same answers. That is totally okay. But again, my focus for today is about learning this method, so I'm showing you why it's useful and where we could use it. Later on, when you're solving a quadratic and it's just all you on your own, you can choose which method's going to benefit you at the time. We're just making sure that you see all of that. Okay? All right, so any questions about how I got these 2 solutions? Danny?
In the blue part,
Uh-huh.
6 squared,
Yes.
does that include both the 12x and the 36?
Yeah, so it does because x plus 6 times x plus 6. Remember, you can't just square the x and square the 6. You get the x squared and you get the 36, but you also in this multiplication get a 6x that's being combined with another 6x. So it does account for all of that because of the foiling or the distributive process that you go through. Okay? All right. So if we want to try to use this method that we're seeing, do you think every problem they give you is going to be as nice as the last one? Like they're just going to give you x squared plus 12x plus 36, like that it's already a nice perfect square ready to factor that way? No. Okay? Which means if I want to use this, I have to learn what I could do to it to tweak the numbers slightly to make it so that it will factor as a perfect square. So if they're not giving me the right numbers, I'm going to put the right number there to make it a perfect square. I'll make sure I don't do anything mathematically illegal, okay? If I put a number on one side of the equation, I better put it on the other side of the equation too. But I can put whatever number I want there as long as I always even it out, okay? So when we look at this equation, x squared plus 18x plus c. Right now we're just practicing making things perfect squares. So basically if I have x squared plus 18x plus c, and I want this to be something that eventually factors to a perfect square, the question is, what number should be in that spot where c is to make it a perfect square? Delaney?
9.
Okay, so you're perfect. Okay, but it's really important what she said. First her brain goes to 9, and then her brain goes to 81. So somebody tell me, why does our brain go to 9 first as an important number in the process of what we're picking? Lauren? So remember when Danny asked about the question about does x plus 6 squared capture like the 12x and the 36? And it did because when we multiplied it out, we saw there was a 6x and another 6x that were making 12x. If we're going to make perfect squares, meaning these are going to be exact replicas of each other, you need whatever number this is to show up twice and add together to make the middle number that's in the equation, right? So when we look at this one, we're looking at 18 and we're saying, oh, if it's supposed to be exact same numbers making 18, what two things must it be that are adding together to make 18? Well, it must be 9x and 9x if they're going to have to be the exact same thing. That's because I'm trying to make a perfect square. If I wasn't trying to make a perfect square, there's lots of things that add up to 18. If I'm trying to make a perfect square, I need two of the same. They'd have to be 9s. Okay? That means that in order to get this, I want basically like an x plus 9 times an x plus 9, because that will give me the 9x and the other 9x. Okay? That means the number at the end spot right here is not going to be 9. The number in the end spot is going to be what that 9 times the other 9 ended up being multiplied together. So it would be 1 would be my C value for this equation. Okay, so I would say 81. Okay, Kenny.
I was looking at, because sometimes won't they have to be positive and not negative?
They. What is
Like
they?
X. Because for the
They have to be.
example 1,
Mhm.
I was looking at that equation,
Uh-huh.
and I just did it for practice, and it
Uh-huh.
was x equals positive or negative 2.
Okay.
But if you plug negative 2, that would be the same.
It's okay? Okay.
Yeah. Figured it out.
All right. So let's generalize the process of what we did. So our eyes first went to the 18. Okay, so that means what they looked at the B value in the standard form of the equation. Okay. Then our brains turned 18 into 9, essentially. We're like, we need 9. Okay, what were we doing to 18 to decide we needed 9? Dividing it by 2. So we're taking this middle term of B, we're dividing it by 2. That's giving us 9. But 9 is not the number we write at this end spot. How did I get 81 from 9? Squared it. This is kind of a mini little formula you can do to complete the square. One issue, this only works when the lead coefficient is 1. If there's a 3 there or a 5 there, that messes up the whole process. Like, how do you make a perfect square with a 5 there? You don't. You got to factor the 5 out, okay? So essentially, we're going to make everything have a 1x squared here. Then we can use this process to figure out this number at the end, okay? So if I look at the second example, r squared minus 9r plus c, and I'm trying to figure out what goes in the c spot, let's walk through this process that we've determined we do. Our coefficient's 1, so that's good. Our I should go then to the b, the negative 9. So we want to take the negative 9. That's our b value. We want to cut it in half, and then we want to square it. And this will tell us the number at the end. It's not magic. It's what we did in our heads when we walked through this process, right? We split this up into 2. We knew that was a good number, but then we needed to square that number to get what's at the end. We're doing that all in one step right here. Okay? So 2 doesn't go into 9 evenly. That's fine. Keep it as a fraction, because you won't always have your calculator to use on these. Okay? So 9 over 2 squared is going to be 81 over 4. In this problem, I would want C to be 81 over 4. It's okay that it's a fraction. Okay? If you're not sure if you're right, check it. If 81 over 4 is the end number, 81 over 4 was made by 9 over 2 squared. Then I'm saying I think that this is how it's becoming a perfect square. In this case, I would have a minus in the middle when I factor it. That's because I want the middle terms to work out to be negative 9. And then multiply this out and see what you get. So if I take r minus 9 over 2 times r minus 9 over 2, again, right now I'm just checking, okay? This was the only work to get the answer in this problem. But just for those of you that are a little skeptical, okay? This would give us r squared. This would give us negative 9 over 2r. This would give us another negative 9 over 2r. And this would give us a positive 81 over 4. Okay? Negative 9 over 2 plus negative 9 over 2 is negative 18 over 2. And what's negative 18 over 2? negative 9. So it did work if I use 81 over 4 as the last number. Okay, it does factor as a perfect square like this. Okay. All right, the last one's more complicated. What's the matter with it? Yeah, stupid coefficient. Okay. So we said we can only use this whole b over 2 and then square it to figure out the mystery end number that you want if it didn't have a coefficient. So basically, I need to factor out that coefficient and work with the problem as if the coefficient wasn't there. So if I factor it out, I would have r squared. If I've taken 2 out of negative 18r, I would have negative 9r, and I'm trying to figure out what should go here at the end. Okay. Lauren? Yeah, so I'm not going to actually write that right now. You're totally fine. That's fine. Okay? But I'm just going to let us figure this out, and then we'll go back and look at what to plug in for C. So how do I figure out what number should go here in order to make this a perfect square? Savannah? We can solve for the number that should be in the C spot doing what? What did we just do in the other two problems? How do you figure out the number at the end that would complete this polynomial and make it a perfect square? Ben? Good. Okay. Same thing that we did before, because now the 2 is gone, right? So we have actually the exact same problem we had in part B, right? Once we look at it without the 2. So I'm going to take the b value, divide it by 2, and square it. Okay? And that's going to give me a value of 81 over 4. So 81 over 4 is the number that I would use to complete the square. But does that number represent C? No. If I wanted to represent C, what could I do now to my expression? Sean? Yeah, just multiply the 2 back through now that you finished the process and see what happened, right? So if I multiply the 2 back through, I get 2r squared minus 18r plus, yeah, and the 2 and the 4, can I cross cancel that? Are we okay with that? Okay, so it'll be 81 over 2. So what was the right C value to complete the square here? 81 over 2. Was it apparent to use 81 over 2 in the original problem? Maybe not, but if there's a coefficient, as long as I factor it out, I can work with this to complete the square using the same method we did when there wasn't a coefficient. Okay? So any questions on, if you're looking at a polynomial, how you would determine the number that you should put as the constant to make it factor as a perfect square? All right. So then let's try to actually do it. Now, the first one's totally factorable. I know that. Okay. Again, my goal is not in the future to dictate which method that you solve by, but right now we're going to say solve by completing the square, and this is why. I want you to be able to solve by factoring. I want you to be able to solve by completing the square. I want you to be able to solve by using the quadratic formula. And then when you're given a problem, I want your mind to be in a place where you can say, oh, it looks like this. I bet I can do this, and it's faster and easier for me. Okay? So I want you to be able to do all of them because they're useful for different things at different times. However, okay, I want you in the end, you're going to choose what you want. But I need you to practice completing the square so I know you're good at it. Okay? So if I'm going to solve this problem by completing the square, I look at the problem. Remember, that means I want to factor the polynomial as a perfect square. Does x squared plus 2x minus 120 factor as a perfect square? No. 120 is not a perfect square number, and it's a negative 120. There's no two exact things that are going to multiply together and make a negative anything, because one would have to be positive and one would have to be negative. So what I'm going to do is I'm going to move the 120 to the other side of the equation because it's not the right number to make a perfect square. And I'm going to put my own number in the equation. Okay? Totally okay, as long as I don't break any mathematical laws about how equations work. So what number would be the right number to have been sitting in that spot to make it a perfect square? Sean? Okay, so 121 would be a perfect square of 11, but then the question is, Is 11 going to help us make the 2 in the middle right here? No. So if we don't change the 2 and we have to dictate around the 2, Jason? 1. So remember, what we're doing is we're taking this, since we're not changing that number, we're dividing it by 2, and then we are squaring it, right? The same process we went through last time. So 2 divided by 2 is 1, and 1 squared is still 1. So I'm going to add 1. Now, that's okay and it's not okay. I can do that as long as I do what else? Lauren? Good. I can add whatever I want on one side of the equation. You guys do it all the time, as long as I also do it on the other side of the equation. So that's fine. Over here and do this. Okay? So again, remember why you did this. You're not stuck at this point. The only reason we added our own special number here was to make this factor as a perfect square, which means my next step should be to factor it as a perfect square. Okay? So how is x squared plus 2x plus 1 going to factor? Good. It should be x plus 1. If you're having a hard time there, when you're doing perfect squares, right, it's like what squared makes this, x. What squared makes this, 1. Do I need the middle terms to end up being positive or negative? Positive, so this should be a plus. Okay? And then on the other side, I have 120 plus 1, so that is 121. And now I have an equation like we did at the beginning. I can solve this by taking square roots. So I'm going to go ahead, take the square root of both sides. So I'm going to get x plus 1 equals, remember I'm going to include plus or minus because I had an unknown thing underneath the radical, so I don't know if it was negative or positive when someone squared it to get this number. 11. I'm going to subtract 1 from each side and pay attention to what that means. That means you have negative 1 plus or minus 11, and that you have 2 calculations to do to finish this problem. Negative 1 plus 11 is 10, and negative 1 minus 11 is negative 12. I know that you could have gotten this answer much faster by factoring. Okay? Totally get it. And you can do that on a test. But I also want you to be able to do this. You'll see more places it's useful as we move through the unit. Okay? All right. What about part B? What would we do first? Ashley? Okay. So first of all, we don't want the coefficient there. We can't use our process of completing the square. So a good strategy might be to divide everything by 2 first. So that would become x squared. The 7x would be 7 over 2x, and the 12 would be 6. Then remember, in our goal of solving by completing the square, we want a perfect square polynomial. Is x squared minus 7 over 2x plus 6 going to factor as a perfect square? Is there anything squared that equals 6, like a whole integer number? No. Okay, or a fraction. It's rational numbers? No. So we're going to move the 6 over and make space for whatever it is that we want to be there. All right, so don't be scared by the fractions. Follow the process you know is going to help you. What was the process we established to decide which number should be sitting at the end of the polynomial and make it a perfect square? What do we look at? What do we do? Kenny? Good. Good. So in this case, our b is negative 7 over 2. That's our b. We want to divide it by 2, and then we want to square it. Okay. All right. Negative 7 over 2 divided by 2 is the same thing as negative 7 over 2 being multiplied by 1/2. Okay? So that is negative 7 over 4 once we divide it by 2. And then we still have to square it, so we're going to get 49 over 16. That's totally okay as long as I add that to the other side. So you guys might hate fractions, but when you're using this process, they're actually not that bad and usually end up working okay in the end. Because when you go to factor it, you don't have to think too much. Remember, now it should factor as a perfect square. X squared is what you have at the beginning. At the end, you have 49 over 16. What has to be squared to make 49 over 16? 7 over 4. And then you look in the middle. Do you want the middle terms to be negative or positive? Negative. So there should be a minus sign there. Okay. Here, you do have to make a common denominator. So this is the fraction math you do have to do. So I'm going to multiply this by 16 to have a denominator of 16. And 6 times 16 is 96. Okay. So I get negative 47 over 16. Okay. All right, once we have our perfect square, to solve the equation, we take the square root of both sides. So we get x minus 7 over 4 equals plus or minus, what is the square root of negative 47 over 16? Yeah, no solution. Why? Because it's negative. The fraction's not a big deal. Square root of 16 is 4. This is why it's actually nice to keep them in fraction form. Because you were completing the square, you usually have a number that has a nice perfect square denominator, and taking the square root of it is not a big deal. And if we had to leave rad 47 in the numerator, that's not a big deal either. When you use quadratic formula, you have radicals left in there, right? That's fine. You would just leave rad 47. The big deal here is the negative. Okay? So we can't calculate this radical as of right now. Some of you took the summer class or have some other exposure. So you know we're going to get to a point where we're going to expand our number system a little bit and look at some imaginary numbers, and we could write a solution to this. Okay? But in this case, and where we are right now, we're not going to say there's no solutions in total, because there are some lurking out there, but there are no real solutions. In the real number system, you cannot calculate the square root of a negative number. Okay? Is this all right with everybody? Okay. Yeah, those of you that know imaginary numbers, we could totally do that. Yeah, Jake. We divided everything by 2 in the very first step. So we divided the entire left side by 2, so x squared minus 7 over 2x plus 6. And then when we divide the right side by 2, 0 divided by 2 just stays as 0. Okay? So remember, with an equation, if you're solving an equation, you can do whatever you want as long as you do it to both sides. So the fact that we got rid of that 2 is fine because we divided both sides by 2. Okay? All right. Last thing that we need to be able to do is to write equations in vertex form. So there's actually 2 ways to do this. One of your homework problems already asked you to write equations in vertex form. And there's a way for you to look at a standard form of an equation and find the vertex. What is the way that we can find the vertex from the standard form of an equation? How many? Yeah, negative b over 2a will give you the x coordinate, and then you can plug that back in and get the y coordinate. And you already have an a value, right? Like in part A, what's the a value of the equation? 1. And then in part B, 2. So there's your A, and if you found the vertex, you have your H, you have your K. You could write it in vertex form. Okay? Completing the square also helps you because, remember, vertex form looks like this. So the whole thing that makes it vertex form and not standard form is the fact that everything is wrapped up in that perfect square. So if you can make a perfect square, you can make something in vertex form. So we're going to go over another way to make vertex form using this completing the square process. If you're like, I don't have to listen because I understand how to find it the other way, that will serve you well now. But later when we're looking at like equations of circles or something like that that have 2 perfect squares that you need to complete, you can't just find like the vertex and write it in vertex form without knowing how to complete the square. All right, so this is going to be here, but it's also going to show up later. So make sure that you try to grasp the idea. All right, so x squared plus 10x plus 27. We want to get everything that's part of the perfect square quadratic together. So everything that contains x, we want it to be part of a perfect square we can factor. Is x squared plus 10x plus 27, the way it is right now, a perfect square trinomial? No. Okay, it can't factor. It can factor maybe? I don't know. Okay, maybe not. Okay. But even if it could factor, unless it factors as the same 2 things squared, right, that's not going to work. And there's no way that's going to happen with a 27. Okay? So you can either move the 27 to the other side. But we don't really want anything on the other side, right? We still want y by itself in vertex form. So if you want, you can just kind of move 27 away from the group you're working with. And what I mean is, I'm not doing anything mathematical to the equation. I'm just changing your perspective right now. You're thinking about the x squared and the 10x as part of a group that's going to make a perfect square, and that the plus 27 is not part of that group because it's not the perfect square number. So I've done nothing to our equation right now, right? It wouldn't matter whether these parentheses are there or not. It's the same thing. But I'm just changing the way you're looking at it, right? The stuff inside the parentheses is going to eventually become our perfect square. And the stuff outside the parentheses can be there, like our plus k stuff, but it's just going to be some other constant value. Okay? So then the question is, what other number do I want inside these parentheses to make this part factor as a perfect square? Good, 25. Somebody tell me how she got 25. Sean? Good. Okay, so b over 2 squared. 10 divided by 2 would be 5. Squared would be 25. Now, I have put plus 25 in this equation. I have literally added 25 to the right side of the equation. That's okay, but I need to keep my equation balanced. So what should I do here? Lauren? Okay, so you have two choices. You either need to also add 25 to the other side, but if you don't want to put stuff on the other side because you just want to keep y over there alone, what can I do on the same side that will help undo the fact that I've added 25 to that side? I can subtract 25. If I've added 25 to one side of the equation and at the same time I've subtracted 25, have I really changed the equation? Not its value. It's worth the same because plus 25 and minus 25 add nothing of value to the equation. But am I changing the way I'm packaging it and the way that looks? Yes. Okay. So you could either add 25 to the other side and then bring it over later, or you can do the two operations on the same side, just make sure they are operations that undo each other. Okay? So remember, I added 25 specifically so that this package could become and factor as a perfect square. So I'll factor that. And then I just need to adjust my constant. It's no longer going to say plus 27. That wouldn't make sense. I have to incorporate now that minus 25. So it's just going to say plus 2. So these two equations, the original one you see up there and this one, are the same exact thing. It's just that's how it's written in standard form, and here's how it's written in vertex form. If you multiply out this perfect square and add 2 to it and combine all your like terms, you will get the exact same thing that you see up there. Okay? All right, what's going to be harder about part B? Yeah, the coefficient of 2. And then here's the bummer. In the last problem, when there was a coefficient of 2, we just divided everything by 2, right? That worked out well because there was a 0 on the other side of the equation. So when you divided 0 by 2, still just was 0. And then our 2 was gone because we were allowed to divide both sides by something. In this problem, I don't really want to divide both sides by 2 because I don't want the left side to say y over 2, right? That's not what I'm supposed to get. So I am going to factor out the 2, but it's going to sit there. It's basically like this a value right here. That's going to be its spot or its home. Okay? So I'm going to have y equals. I am going to factor the 2 out. But you know what? I'm going to write one step in between so that you guys understand. The stuff with the x's is going to try to be making our perfect square package, and the constant is going to be like our k value out here, right? Just like we did before. But then we're saying we can't do it with a 2 in here, so we need to factor the 2 out of this polynomial. So I had 2x squared. If I factor 2 out, 2x squared divided by 2 leaves me with x squared. I had 7x, and I'm factoring 2 out. That means take 7x, divide it by 2, and write down what you would have left, which means I would have 7 over 2x. What's staying at the end right now? Plus 10 or plus 5? 10 still, right? Because it's not part of the group where I'm factoring the 2 out of. Okay? Because it's not part of that parentheses or that set. So I'm still going to keep this valued at 10. Okay? Because I separated it with that set of parentheses from the other terms. All right, so how do we figure out what number goes here? Savannah?
Multiply by 1/2 times.
Good. So you take your b value, you divide it by 2, and you square it. So we established that dividing by 2 is the same thing as multiplying by 1/2. So I'm basically going to have 7 over 4, and I want to square it, so I'm going to have 49 over 16. All right, I wrote 49 over 16, but I didn't actually add value of 49 over 16 to the equation. Can anybody tell me how much value I actually added to the equation by writing 49 over 16 in that spot? Jason? Okay, he's saying I actually added 98 over 16. Where is he getting that from? Michael? Yeah, A was here. I wrote 49 over 16, but what's really happening to that? It's getting multiplied by 2. So my pencil might have wrote the number 49 over 16, but I actually added an amount of 49 over 16 times 2. Does that make sense to everybody? Okay, so you got to be really careful with what you decide to put right here, because what you wrote down, you don't get to go on autopilot. I wrote this, I write it again. Okay, you got to pay attention. When you wrote it, was it getting multiplied by something? Okay, so instead of calling it 98 over 16, is it okay if I call it 49 over 8? Because like the 2 times the 49 over 16, the 2 would cancel the 16 and leave an 8 in the denominator. Okay, so 49 over 8 is the amount. I added it, and this is on the same side, so if I want to kind of undo what I've done, I'm going to subtract it here. Okay. All right, and then I just have to write it in the correct package, meaning this stuff is supposed to be a perfect square now, and I got to deal with adding together those constants at the end. So remember how to quickly factor it. If you've done your perfect square operations correctly, we have an x. What squared makes 49 over 16? 7 over 4. We want the middle terms to be positive, so there should be a plus. And then you are going to have to do a little bit of fraction arithmetic over here. Okay? So I want a common denominator of 8 to add these together. So times 8 times 8. So I basically have 80 minus 49. So 80 minus 49 is 31 over 8, and that's it. At least if you're rewriting it in Vertex Form, you don't then have to go do anything with those fractions. You just have to get them in that spot, okay? So is this all right? So completing the square can do 2 things for us. It can help us transfer forms of the equation standard to Vertex Form. Okay? The other thing it can do for us is it can give us another option of solving. Again, when I'm not saying you have to use completing the square, I'm going to say it at first because I want you to get some practice. When I'm not saying that and you make the choice, this wasn't a bad problem to use completing the square to solve, right? It wasn't too hard to add this number. It worked out nicely. I don't know if I was given the choice if completing the square is really what I would use over here, okay? But when someone tells me I have to, because we need to learn how to do it for this purpose and for future purposes, then that's what you'll do for now, okay? So homework 6.